Dear students, in last class we completed comparison of AC and DC transmission and distribution systems on the basis of the volume of conductors used. Today we will take up economical size of conductor. Now look at the distribution network shown in figure here. Here is a main substation and here is secondary substation. Between main substation and secondary substation, you can see a conductor called as feeder. So you can define feeder as a circuit carrying power from main substation to secondary substation such that the current loading is same throughout its length. Because you can see here between main substation and secondary substation there are no loads connected, and hence current through this feeder throughout its length remains the same. After secondary substation you can see a conductor called as a distributor. On distributor at various points loads are connected. You can see here several loads connected, which means that current in this distributor is not constant throughout its length. Before the first load current is maximum. After the first load current gets reduced. After the second load the current gets reduced further, and so on. Such a distribution network should be capable of maintaining the terminal voltage of consumers within plus or minus 5% of the specified voltage for the satisfactory operation of appliances. Therefore, in case of distributor, the allowable voltage drop decides the cross section of the conductor, whereas cross section of a feeder is decided on its current carrying capacity. So I will mention those 2 points here. The allowable voltage drop decides the cross section of the conductor used in distributor, whereas cross section of of the conductor used as feeder is decided by its current carrying capacity. Now, our aim is to determine the economical size of the conductor used as a feeder. For that, we make use of Kelvin's law. Kelvin's law gives the cross section of a feeder conductor based on an economic balance between capital cost and operating cost or running cost. The annual capital cost of an overhead line include interest and depreciation. Cost of conductors, insulators, supports, and their erection, etc. The annual capital cost of underground cables consists of cost of conductors, cost of insulators, and the cost of laying the cables. For overhead lines, the cost of support and erection may be partly constant and partly proportional to the cross section of conductor. The cost of conductor is proportional to area of cross section for both the overhead line and underground cable. Thus, the annual capital cost can be represented as C1 plus C2A, where C1 and C2 are the constants and A is the cross section of conductor. The running cost of a feeder is the cost associated with the energy wasted in the conductor the annual cost of energy wasted in the conductor is due to resistance and due to dielectric loss in insulation and the loss in sheath in underground cables. Since ohmic loss is inversely proportional to the area of cross section as resistance R is inversely proportional to area of cross section. The annual cost of energy wasted can be represented as C3 by A, where C3 is a constant. Thus, the total annual cost and the cost of energy wasted per annum becomes C equal to C1 plus C2A plus C3 by A. Let us call this as equation 1. For economical cross-sectional area of the conductor, that is feeder, the total annual cost must be minimum. That is differentiation of total annual cost with respect to area of cross section must be equal to 0. Differentiating, we get 0 plus C2 minus C3 by A square equal to 0, or C2 equal to C3 by A square, or A square equal to C3 by C2, or A equal to under root C3 by C2. Or C2A is equal to C3 by A, which means the variable part of capital cost must be equal to the cost of loss of energy in a year for the most economical working. Now we will show the variation of cost of conductor with variation of the area of cross section. Along y-axis annual cost is taken, and along x-axis area of cross section of conductor in centimeter square is taken. Let us say the fixed cost is C1 and cost proportional to cross sectional area is C2A, if we add C1 and C2A, we get C1 plus C2A. the annual cost proportional to loss of energy, which is inversely proportional to cross-sectional area, may be shown like this. Now if we add the C3 by A to C1 plus C2A, we get a curve which shows us the total annual cost, and the total annual cost becomes minimum when C2A and C3A are equal. So this is the point at which C2A is equal to C3 by A, and this point gives us the economical size of the conductor or feeder. Now we can add here the condition for economical size of conductor is the variable part of annual capital cost must be equal to annual cost due to energy loss. Dear students, I will stop the class here and continue in next class with the limitations of Kelvin's law and a problem based on Kelvin's law. Thank you.